Hello and welcome to Unit 8, Part 5. My name is Mr. Bell, and today we're going to talk about absolute value equations and inequalities. Before we actually work some examples, I want to talk a little bit about absolute value and kind of refresh your memory. Absolute value is represented by these long, straight, vertical bars around numbers or expressions. They do not have the same meaning as parentheses do, so be careful. These bars are absolute value bars, and what they mean they're asking you to figure out how far is what's inside of it from zero. The distance from zero on the number line is what absolute value stands for. So if I'm asking you for the absolute value of -3, what I'm asking you in a different form is how far away is -3 from zero? Well, it's 1, 2, 3 units away. That's why the answer to the absolute value of -3 is a +3. If I were to ask you what's the absolute value of +3, it's asking you the same kind of question, except how far away is 3 from 0? And even though I'm going to the left, I'm still taking 1, 2, 3 steps or 3 units away from 0. So the absolute value of 3 is also 3. Both of these numbers here are 3 units away from 0 on a number line. Now I know this is a little tricky, but I want you to think of it like this. What if I wrote a variable in the absolute value bars is equal to 3? Well, if you recall from our previous example up here, there were two possible answers that x could be. X could be equal to a -3, or x could be equal to a +3. Both of those values, if I plugged them in for x, would give me a true absolute value equations. They would both give me the result of 3. So keep that in mind as we solve some of these more complicated equations, absolute value equations. In this first example, we're asked to find the absolute value of x plus 7 is equal to 10. We're basically solving this thing for x. Well, think about it from the previous example. I don't know what the value of x is at the moment, but I know inside of these absolute value bars, x plus 7 is either going to be equal to 10 or -10, because I know both of those values are 10 units away from 0 on a number line. So the way I'm going to solve this is I'm going to set x plus 7 equal to 10, because that's one of my options of what could be the correct answer, or x plus 7 could be equal to -10. If I got -10 in the absolute value bar, the absolute value of -10 is a +10. So this is how I'm going to solve for what two possible answers for x satisfy this equation. On this first one on the left, I'll subtract this 7 from both sides. One of my values is a 3. And the other possibility is if I subtract 7 on this one, -10 minus 7 would give me a possible value of -17. Both of those values, or either of those values, if I replaced x with them, would give me an absolute value function that is 10 units away from 0 on the number line. On this example, we have absolute value of a minus 3 is minus 5 is equal to 4. Now, before you do the same thing we did on the previous slide, you need to isolate the absolute value bars. They are not like parentheses, so we don't need to distribute or anything like that, but we need to isolate it on one side of our equation. I'm going to do that by moving this -5. The way you undo that operation is by adding 5 to both sides of our equation. That removes it, in theory, from the left side, leaving me with the absolute value of a minus 3. And on the right side, when we move that 5, 4 plus 5 gives me 9. Now I can solve this absolute value equation just like the last one. I don't know what a is at the moment, but I know inside of this absolute value bar can either be 9 or -9. Those will both provide me an absolute value solution that is 9 units away from 0. So let's set up two equations to solve. A minus 3 could be 9, or a minus 3 could be equal to -9. And let's solve them. This first one, I'll add 3 to both sides, giving me an a value of 12. And on the second equation, I'll add 3 again. This time I'm adding 3 to a -9, giving me a sum of -6. Both of those values could plug in for A and give me the absolute value equation that I'm looking for. Notice on this next example, we have an absolute value inequality. So there's a little trick that you have to remember with inequalities. So to begin with, I always write one equation just like it's written, but without the absolute value bars. Meaning I'm going to write x plus 3 greater than or equal to 7. Looks just like the original function, but without the absolute value bars. Now the other one that we have to write is going to be x plus 3, and we have to flip our inequality and change the sign of the value on the right side. That's the same, kind of the same concept of when you multiply or divide both sides of an inequality by a negative number. You have to remember to flip the inequality sign. Well, that's kind of what we're doing here. Now I can solve my absolute value inequality for the two possible solutions. I'll subtract 3 on this left one, meaning that x could be a value greater than or equal to 4, and this would make a true absolute value equation. Or I could subtract 3 on this other one, giving me a set or a range of values that are less than or equal to -10. So the key feature there to remember is when you make your second inequality, you flip the inequality sign and you change your value to a negative. On this last example, I wanted to show you or demonstrate graphing graphing absolute value functions, just to show you what they look like. Well, absolute value functions tend to make a V type shape, and it could be a V like this one, or it could invert the other way. But I want to remind you about transformation rules and kind of bring that back into play from our quadratics chapter. Well, if you remember from way back then, whatever value we had inside of our parentheses for that quadratic described a left or right shift opposite of whatever it was. So if we had a +5 in here, that actually meant a left shift of our vertex 5 units. And whatever value was on the outside, like -4, meant an up or down shift, and it would be the same as whatever that is. So this would be a down 4 transformation. So we're going to use those same rules to apply here, but we're going to kind of work backwards. If we look at our vertex from this function that's graphed up here, it looks like they went right 3 and down 2. So I've got to kind of use that transformation mentality and see which of these functions match. Well, I remember that the outside of the parentheses is exactly what you would think. Down 2 would represent a -2, so that eliminates C and D because they are +2. Now we got to figure out which function represents a transformation or a translation to the right 3 units. And remember that that's the one that's tricky. That's the one that's opposite of what you would think. So in this particular case, to go to the right 3 like our vertex did, we need to do the opposite of +3, which is a subtract 3. Now, that is a transformation pattern, which is good to remember and good to know. But guys, you could also very carefully type this in your calculator and look at the graph and try to observe which graph matches the function that you're looking for in your answer choices. So just remember, whatever inside the grouping symbol is a left or right shift opposite of what you would think, meaning a +3 actually means to go to the left 3, and a -3 actually means to go to the right 3. And then the outside values from your grouping symbol, your brackets, your parentheses, or your absolute value, it's a vertical shift up or down, the same that you would think. -2 means down 2, +2 means up 2. All right, thanks for watching. Hope this helps.